Okay. Hey, everybody. Thanks for coming to another EERI seminar. Today we've got Dr. Sumin Ham. Right now she's a postdoc at UC Davis. She got her PhD in South Korea in 2021, focusing on different cementation characteristics of and erosion behavior of biocemented sands. And right now she's focusing on sustainable improvement methods for microbially induced calcite precipitation, which we'll be talking about today. And those applications in earthquake engineering. She also has a lot of background in multi-hazard loading, sustainable bio-inspired geotechnical engineering, energy geomechanics, and other geotechnology. So with that, we're very excited to have her, and please take it away. There you go.
Hi, thank you, Noah, for the kind introduction, and thank you for everyone coming here. My name is Sumin Ham, and I'm a postdoctoral researcher at the University of California, Davis. And today I'm going to talk about the microbially induced calcite precipitation for liquefaction mitigation, mechanisms and impacts from the microscale to macroscale. Background of the research. So I did my PhD in South Korea at KAIST. And at that time, I did the research about the MICP as well. So I started from the particle level studies, and expanded to the soil erosion behavior. And then I moved to the UC Davis to do my postdoc. And here, UC Davis, they're more into the earthquake engineering. So I started to do my research, something related to the liquefaction mitigation as well. So I will present some part from my PhD work and some part from my work at the UC Davis.
Click on the presentation. Yeah, there. Thank you.
So here is the background of the research. So nowadays, the climate change caused many nature disasters, and this figure shows the natural disasters happened in 2023, which caused the overall losses of $250 billion US. And all these disasters can be categorized by the source. The first one, the geophysical events like earthquake, and meteorological events like storm, and hydrological events, and the climatological events. But if you focus on the red one, which is the geophysical events, you can see that there are many seismic events occurring along the fault. So as geotechnical engineering, we have to design by considering the higher performance demands and consequences. So let's focus on the earthquake liquefaction. So soil liquefaction is a phenomenon where the saturated soil loses its strength in response to the earthquake and behaves like a liquid. And as you can see in this figure here, the consequences to the structure include the excessive total and differential settlement, lateral displacement, and structure tilt. This can cause a huge damage. So many improvement methods are developed to reduce and minimize the consequences to the structure. Among them, the biocementation technique can be used as a sustainable soil improvement technique. So microbially induced calcite precipitation, also known as MICP, use the bacteria which has the urea gel. And this urea gel can decompose the urea into the carbonate ion. And when this carbonate ion meets the calcium ion, it precipitates chemically stable and low solubility calcium carbonate. And this precipitated carbonate changes the soil properties through the cementing at the particle contact, and coating of grains to increase the density, and roughening of grains to increase the dilatancy. So it can hold the soil particles together during the shaking, therefore preventing the liquefaction. So in this talk, I'd like to present the effects of the biocementation on liquefaction triggering at different scales to understand and validate the effectiveness and the implementation of MICP treatment across the various levels of the complexity. So first started with the micrometer scale, which is the particle scale. So we can understand the fundamental interactions at the particle scale. So insights from this scale help predict the behavior of the MICP treated soil, providing a foundation for the upscaling to the larger system. And at the element scale, which is the lab test scale, we can observe the behavior of the soil elements that represent the manageable portion from the large system. And this scale test provides the crucial data for engineering application and model validation. The last one, at the system scale, we can evaluate the performance of the MICP treatments on a larger system. And this ensures that the insights gained from the smaller scale transfer effectively to the larger and more complex systems. And it evaluates the performance under the real conditions. So this systematically progressed from the particle to field scale, bridging the gap between the fundamental theory to the field application. So let's start it with the grain scale cementation characteristics of MICP treated sand. So particle level study offers a fundamental understanding of the cementation characteristics of MICP. So in this study, we measure the tensile and shear strength of the MICP treated particles, and also the precipitation pattern and the failure mode were investigated. And let me start it from the experimental setup. So in this study, the glass bead having a diameter of 3 millimeters was used to minimize the variability between the soil samples, so we can clearly observe the trends in the experimental data. And these glass beads were packed into the soil column, and MICP treatment was applied. So after the treatment, as you can see here, the glass bead became a solid soil column. And this is split into the bead pairs, which consists of the 2 glass beads with the precipitated calcite, like this figure. And we measure the weight to get the exact calcite content for each bead pairs. And we also took X-ray CT image to quantify the precipitation pattern. And 30 glass bead pairs were used for tensile and shear tests, respectively. And this is the test setup for the tensile strength test. And in this red box, the glass bead pair was located. And one side of the glass bead is attached to the deformation control beam, which implemented the horizontal displacement. And the other side was mounted to the rigid cantilever beam, which is instrumented with the strain gauges. In this way, we can measure the load applied to the sand particles during the test. And if you look more detailed this part, you can see the sand MICP bonding is exposed to the tensile stress. And for the shear strength measurement, we reoriented the direction of the particles so that they can expose to the shear stress. And this is the representative result from the tensile test. And you can see in the video a beam moving to the right until it failure. And you just see the failure happen. And this is the time versus force curve obtained from the strain gauges. And you can see the force increased as the bead pair resist the tensile force until the bond breaks. And here we define the failure force as the maximum force. And in this case, it was 55 millimeters. So let's start it with the failure mode analysis and then the bonding strength. From the test, 3 failure modes were observed. The first one is the debonding failure, where the failure occurred between the sand particles and the precipitated calcite boundary. And then the second mode was internal failure, where the failure occurs within the calcite. And the third one is the mixed failure, which is in between. And if we go back to the first time graph, depending on the failure mode, you can see the red one from the debonding failure requires the highest force to break the bond, while the black one from the internal failure requires the less force to break the bond. And this can be explained by the concept of the surface energy. So surface energy is the energy to create a new surface. So from the previous researches, it has been found that the energy required to create the new surface within the calcite is smaller than the energy required to create the new surface between the calcite and silica. So that aligns with our experimental results. So we know the force and we know the area, so we can calculate the bonding strength. And this is the bonding stress versus the calcite contents in the x-axis. So calcite contents is defined as the mass ratio between the precipitated calcite and the sand grains. So here we are using a uniform size of the sand particles. So higher calcite contents means more calcite was precipitated. And there are variance in the data, but you can clearly see that the debonding failure has the higher tensile strength than the strength from the internal failure. And this is the strength distribution curve. The strength due to the debonding failure, which is the red one, located at the right side with the higher mean tensile strength, and then the strength from the internal failure located at the left side with a lower average tensile strength. Next analysis is the precipitation patterns. So before we go to the precipitation patterns, let's look the failure surface first. So in this study, the failure surface is defined as the contact area where the two particles joined together with the precipitated calcite. And I told you that I took an X-ray CT image before the test, and this is the result from the X-ray CT images. And this white one is the glass bead, and this black, you can see this black line, which is the calcite precipitated calcite covers the sand particles. And if you look at the middle cross section here, you can see this white area, which was the location where the bonding originally formed due to the calcite. So we are measuring the area of this white section, and we are using it as a failure surface area. And we also plotted the failure area with the calcite contents, and we found that they have a linear relationship. So more precipitated calcite creates a larger bonding area. And based on that, we investigated the precipitation patterns. There are 3 calcite precipitation patterns. The first one is the grain coating. Oh, and this cartoon, the white circle one represents the sand particles, and then this gray one indicates the calcite. So first precipitation, which was the grain coating, is where the calcite precipitates uniformly on the soil surface by coating the grains. And the second mode was meniscus filling, where the calcite only precipitated at the meniscus at the contact. And third mode was flat torus filling, where the additional calcite was precipitated around the contact. And if you know the radius of the soil particles and the calcite contents, then by using a geometrical equation, you can get the relationship between the bonding area and the calcite content like this figure. And this red line is the data from assuming the grain coating precipitation patterns, and the black one from the meniscus filling, and the blue one from the flat torus filling. From this data, we can say at the lower cementation level, the calcite precipitated by following the grain coating patterns, but at the higher cementation level, the calcite precipitated by following the meniscus filling or the flat torus filling. So implications for this study. So we are trying to develop the DM bonding model for the MICP treated sand by using a parallel bonding model. So parallel bonding model transmits the force and the momentum in a normal and shear way. And if you look detail about the parallel bonding model, we need a bonding area for the bonding, which we just measured from our test. And this parallel bonding breaks when the load force applied to the bonding exceeds the critical force that the critical force is the critical maximum tensile strength we just measured from the experiment. So we are trying to develop this kind of the bonding model by using the experimental data that we got. So after developing the bonding model, we are planning to validate our model by comparing with the experimental data that has been already performed by the previous researchers. So we have explored how MICP can change the soil mechanical properties. So let's move on to the element scale to see the dynamic responses. So in this section, I will show you the result from the cyclic direct simple shear test, which is conducted by the Mike Gomez in the University of Washington. I put this section to bridge my particle level scale studies and the system level studies. So this is the result for the undrained direct simple shear test. And the sample was initially prepared in a loose condition with the relative density of 30% with the initial effective stress of 100 kPa. And the results from the upper rows are from the case with the delta Vs of 0 meter per second. And then the second row are the results from the delta Vs is equal to 95 meter per second. So one thing to note is we are using a shear wave velocity as an indicator of the cementation level. So shear wave velocity is directly related to the soil stiffness, which is the shear modulus by G is equal to rho Vs squared. So higher shear wave velocity means higher stiffness of the soil, which is caused by the MICP treatment. And both samples were with the CSR of 0.2. And from this result, we can find that the modest increment in the cementation can substantially decrease the excess pore pressure generation and the shear strain development early during the undrained cycling loading. For example, the number of the cycles to get the RU of 0.95 increased from 0.5 to 650 from uncemented to the cemented sand. And here are more data with the higher CSR level with 0.75 and 1.5, corresponding to the shear wave velocity improvement from 194 to 476. From this test, we found that the number of the cycles to get the higher strain increased with the MICP treatment. And once we started to generate the shear strain, the rate of the excess pore pressure generation became very complementary on cemented sand to the levels of the treatment. And last one, the number of the cycles to achieve the 3% of the shear strain goes up with the MICP treatment. And this is the compiled data for their test. And for the side notes, the liquefaction triggering can be defined using either shear strain and excess pore pressure generation. But previous tests have shown that there is a little difference between the criteria for the cemented sand. So they use shear strain as their criteria for the liquefaction triggering. So here they plotted the data for the delta Vs in x-axis, which is the MICP treatment level, and y-axis is the number of the cycles to get the 3% of the shear strain. And as you can see here, you can see the clear log linear relationship between the delta Vs and the number of the cycles, even at the relatively low magnitude of the cementation. And also you can observe that the applied loading magnitude increase, the effect of the delta Vs increase may become less pronounced as indicated by the trend line with increasingly get flatter. And next figure shows the applied CSR versus the number of the cycles to liquefaction triggering with the different cementation level. So the light color means the less cementation, and this dark color is with the sample has a highly cementation level. And this black arrow indicates that the 10 cycles to 3% of the shear strain, and you get the CSR increase from about like 0.1 to 0.3 with a pretty modest incremental in the cementation level. And the results from the cyclic DSS test suggest that even small magnitudes of the cementation can dramatically alter the soil liquefaction triggering resistance. So now we are done with the particle level study analysis and the element scale analysis. So let's move on to the system scale analysis. For the system scale analysis, I have conducted centrifuge test to see the system performance of the MICP treated sand as well. So let me start it from the history of the centrifuge test that conducted at the UC Davis with the MICP treated sand. So in 2013, Rina Montoya conducted a small centrifuge test, and they found that the MICP can reduce the excess pore pressure generation. And as you can see here, the gray one is the excess pore pressure from the uncemented sand, which is already above the RU of 1. But if you look at the data in a blue, which is from the MICP treated sand, you can clearly see it reduced the pore pressure generation. And 2019, Kate Darby conducted another set of the centrifuge test with varying cementation levels, and they figured out that the MICP has a large effect on CRR, which resulted in an upward shift of the triggering curve from gray one to the blue one. And they moved on to the 9-meter centrifuge test. So Atif Zamani conducted a 9-meter test with the complex soil stratigraphy with a very simple foundation on the top of it. And they figured out that the MICP treatment can reduce the structure total and differential settlements. But the previous 1-meter test was conducted with the sample where the entire container was treated with the MICP, which is not the realistic. So Alex Sampablo coming back to the 1-meter centrifuge test to investigate the effect of the limited improvement step. And she placed the discrete MICP block having a different treatment depth. So in here, PC100 means she treated the MICP block up to the 100% of the liquefiable block, and the PC37 next to it indicates she treated the MICP block up to the 37% of the liquefiable layer. And from this study, she figured out the limited improvement depth can create the base isolation effect. From all these previous researches, provide the unique opportunity to balance the increased structure demand and the reduced structure settlement. So in this study, we'll see the structure behavior with the limited improvement depth. And for the practical design practice, we need to consider these things. First, the MICP improvement depth and the lateral extent, like how deep or how far should we treat, or the MICP treatment level, how much do we want to improve the soil properties, or the what is our target structure's natural frequency, and what is the expected input motion characteristics. But in this study, we just focused on the MICP improvement depth. And this is the setup for the centrifuge test. So Ottawa F65 sand was used, and it was fluvated at the loose condition with the relative density of 38%. And uncemented case was prepared as a reference, and we treated the entire container with the MICP, which we called it as fully cemented, FC, and 2 partially cemented samples were prepared as well. The first one is PC100. So when we are saying the partially cemented, that means we are using a discrete MICP block. And this is the plan view of our container. You can see this light brown indicates the loose layer, and this dark brown indicates the MICP treated block. And you can see we have a 8 by 8 meters MICP block in the center of the container. And if you look at the side view, which is at the lower figure, for the PC100, we treated the MICP up to 100% of the liquefiable layer. So the MICP block is from the dense layer to the top of the soil surface. But for the PC37 model, you can see here, we treated the MICP up to the 37% of the liquefiable layer. So in this case, this MICP block is placed on the loose layer. And we instrumented the accelerometers and pore pressure transducer to monitoring the dynamic behavior during the test. And after building the model, we saturate the model container with the 40 times viscosity fluid to following the scaling law of the centrifuge test. And we did a test at the ADG. Let me give you more details about the structure that we used. So we just used a simple foundation structure, which has the contact stress of 80 kPa. The dimension of the structure was 4 by 6.67 meter. And to monitoring the behavior of the structure during the test, we implemented the high-speed camera system. So it is consist with the 4 high-speed cameras, and this camera system was placed on the top of the container. And they're recording the structure during the test. And on the structure, we put this checkerboard mark so that we can exactly tracking the points. And the high-speed camera can record the video up to 480 frames per second. And this is the test program. So we did a shake sets. We did a 3 shake sets, and we pushed the cone between the shake sets. But here I will show you the result from the shake 5, which was the peak phase acceleration of 0.32 g with the main frequency of 1 Hertz. And our input motion looks like this. Those are the sine wave, but it has 3 building cycles and 5 holding cycles and 12 decaying cycles to mimic the real earthquake motion in a simple way. And this is the video taken during the test, recorded from the camera here. And yeah, with the earthquake, you can see the structure settled with a rocking angle. And here I will show you the result of the sensors embedded in the soil first. So the result that I'm showing you is the sensors at the center array right below the structure. And we installed the 1 ACC at the base of the container to get the input base motion. And for the structure acceleration, I told you that we are tracking the displacement of the structure. And with the second derivative in time, we can get the acceleration of the structure. And this is the pore pressure data from the test. So PPT1 is at the PPT located at the bottom, and PPT5 is the PPT located near the surface. And this is the time series pore pressure data. And the earthquake motion was loaded around 2 seconds. And you can see the pore pressure was generated. And here I also plotted the gray dashed line, which indicates the initial effective stress applied to each sensors. So if this generated pore pressure goes close to this gray dashed line, that means the liquefaction triggered. And those are for the other cases. And the gray background indicates the sensor embedded into the MICP block. So uncemented one, there was no MICP treatment. So all the sensors are in the uncemented zone. So they have all the white background. But if you look at the fully cemented case, all the sensors were embedded inside the MICP block. So I just put the gray background. And for PC37, only the PPT5 was in the MICP block, and PPT3 and PPT1 are at the loose sand, so they have a white background. And if you compare the result from result of a fully cemented case from the UC, you see there is the less pore pressure generated compared to the UC case. And same for the PC100, but it seems like there is the MICP degradation at the lower part of the MICP block. And if you look at the PC37, below the MICP block in a loose stand, they are all liquefied, but the MICP block didn't liquefy. You can tell based on its pore pressure data. So let's summarize that. So you see case, the liquefaction triggering throughout the model, fully cemented model, minimal pore pressure development because it never liquefied. And PC100, there is a limited pore pressure generation at the top, but seems like a cementation degrades near the base. But PC37, there is a minimal pore pressure generation at the top, but underlying untreated soil liquefies. So let's move on to the accelerometer data. So I told you that I put the 1 ACC at the outside of the container to get the base motion. And if you compare the base motion, they are quite similar between each cases. But in the UC cases, it's obviously liquefied. You can tell based on the dilation spikes here. And looking at the fully cemented model, you can see the energy being transmitted all the way up to the top of the container. Additionally, the energy amplification was observed as well. And for PC100 model, it is quite similar to the FC model, but because of the degradation of the lower part, there was a little bit of the energy lost at the end. But still, at the beginning, there is the implication due to the MICP treatment here as well. And in the PC37 model, since the soil below the MICP block liquefied, and this liquefied block observed the energy from the base motion, so less energy was transmitted to the MICP block. So you can see the gradually energy loss without any energy amplification for the PC37 block. And these soil behaviors can affect to the structure's behavior as well. So you can see the higher amplification for the structures on the MICP block, except for the PC37. And I told you lots of energies were observed from the underlying untreated sand. So PC37 didn't experience that much amplification. Summarized once more, you see liquefaction triggering throughout, fully cemented, amplified dynamic loading, higher structure acceleration. Same for the PC100 was similar to the FC model, but PC37, the underlying liquefied soil reduced the dynamic loading of the MICP zone. So isolated MICP zone reduced the structural acceleration. And this is the Stockwell spectrograms for all the models during the Shake 5. So from Stockwell diagram, we can see how frequency evolved over the time. And in this graph, I also plotted the PPT data as well with the white solid line here. And this yellow dashed line is its initial effective stress of the RU of 0.95. And this yellow solid line indicates the 1 Hertz of the motion, which is our input, which is the frequency of our input motion. And if you look at the uncemented model, the limited 1 Hertz frequency was transmitted up to the container. But compared to the UC, you can see in the FC model, it never liquefies, so resulting in the frequency content remaining unchanged as it propagated to the surface. But for the PC100 model, due to the bonding degradation at the lower part, PC100 experienced the frequency changes at the upper part by a little bit. And for PC37 model, the frequency content unchanged until it gets liquefied, but at around the 5 seconds, the frequency content has been changed because of the liquefaction triggering. And you can see at the point when the frequency content changes, you can see the rapid excess pore pressure generation as well. And here are the structure behaviors from the shake 5. Here I plotted the structure settlement in y-axis and structure rotation angles in x-axis. So shake 5, which has the PBA of 0.34 G, was above the structure rocking acceleration. So any structure, so with the earthquake motion, the structure started to rotate. And any structure rotation resulted in the soil below it being subjected to an increased bearing pressure. But the uncemented sand can't handle this kind of the increased bearing pressure, so it just settled without any significant rocking. But if you look at the results from the fully cemented one, the MICP treated sand can support those kind of the increased bearing pressure from the structure rocking, so it rocks a lot and settled less. And PC100 shows the similar results from the FC model with the settlement of 1.1 meter with the rotation angle of 1.3 degree. But if you look at the result from the PC37, it lies between the soil behavior between the PC100 and the uncemented model. So it settled 0.2 meter, but it rotated only 0.3 degree. So from the result here, we found that the partial treatment step produced the reduced structure acceleration as well as the reduced structure rocking and settlement. So this summer we conducted another 9-meter test because from the previous 1-meter test we just using a simple structure and there is no difference between the MICP treatment. So we moved on to the 9-meter centrifuge test with the more complexity settings. So let me briefly explain of our 9-meter test. So we are using 3 different type of the structures. The first one is just a plate, just for the surcharge. And we use the structure A that has a period of 0.32 S. We try to match the natural frequency of the structure to the natural frequency of the MICP treated sand. And third structure was called structure B, and the natural frequency of the structure B was 0.92 second. We are trying to use the 1 Hertz sine wave motion, so we try to match the natural frequency of the structure to our input motion. And we loaded various types of the loading. First, 1 Hertz sine wave, the simple basic one to get the clear data trend. And we also loaded the real earthquake motions. So from this study, we are trying to get the effect of the different structures having different natural frequency and different MICP treatment and different input motion to the soil structure interactions of the MICP treated sand. Yeah. So for the conclusion, these talks cover the effect of the biocementation on the liquefaction triggering at the different scales. From the particle level studies, the particle level test, the cementation characteristics by MICP were identified by analyzing the failure mode and cementation patterns with a DM implication. And for the element scale test, we got the result from the cyclic DSS test, and that suggests that the even small magnitudes of the cementation can mitigate the soil liquefaction triggering resistance. And from the system level scale test, we found that the partial improvement of the liquefiable layer with MICP treatments may be effective in minimizing the structure settlement and rocking without any amplification. So thank you for your attention. And I also like to thank you to our team at the CGM. If you have any questions, I will be happy to answer to any of them.
Thank you very much for the presentation. And yeah, time for questions. I saw Tanner first.
You want me to go ahead? Hello, thank you so much for the presentation. I got a quick question, I'm just curious. So I know that here in Nevada, we have a really bad soil condition that eats away at cementitious material. So with your research, did you do any sort of research on like the interaction between the cementitious material in your tests versus like corrosion or anything like that?
That's a good point, but for this one, I just focus on the figuring out the mechanisms of the MICP treatment. So I just try to use a clean sand, but I think that's a good point. That's the room for the investigate.
Thank you so much.
Yeah.
I'm just gonna ask, is the MICP treatment very expensive to do to like on a broad scale, or is it pretty affordable?
So we have a student who is doing a LCA analysis for the MICP as well, and we always try to get the cost effectiveness of the MICP because that's all the thing that industry people asking. But so we are comparing the MICP technique to the cementation in cement grouting or something like that, right? But if you compare the cost from the cement grouting and the MICP cementation, there is less difference. But you're thinking like, oh, MICP sounds fancy, so it will cost more. But we are trying to use the bacteria that is already exists in the soil, so we do not have to pay for that. We have to pay a little bit to grow the bacteria, to grow the activity of the bacteria, but it will not that cost much. And the chemical that we use for the MICP is not that expensive, just the urea and calcium source. So in terms of the cost, I don't think that will be the problem for the field application.
Cool, thank you.
Thanks for your presentation again. I have a couple of questions actually. When you talked about the failure types, so what are the terms behind that causing having like the different failure types for the cementation that you were talking about, like debounding, mix, and intermediate? It was in slide 10, I think.
I don't know exactly which factor affect to the failure mode, but based on my experiments, at the higher calcite contents, they usually shows the internal failure, and at the lower calcite contents, they usually shows the debonding failure. So maybe the precipitation concentration may be the one of the factor.
But like the way that I understood, when you increase the calcite precipitation percentage, it should increase like the strength of the soil or the cemented soil. But as I see that the bonding right now shows the highest tensile force.
But yes, because so if you can think like more precipitated calcite can create the strong bonding. That's true, but that's only applicable when they are in the same situation. So for the same internal bonding, you have a more calcite, then you will require higher force to break the bond. But if you compare the case from the internal failure and the debonding failure, the energy to make a failure is different. So for the internal failure, you have to break the bond within the calcite, right? But to get the debonding failure, you have to break the bond between the calcite and the silica. But the previous research figured out that it requires some more energy to break between the silica and calcite. So that's the reason it requires a higher force to make it failure.
Yeah, sounds good. And the part that you were talking about, the simple shear test, you were just reporting, presenting the result.
Yeah.
Did they study the liquefaction on the simple shear test? It was like the studying this liquefaction, because as I noticed, the shear strain that was recorded was around peak to peak was around 20%, 30%, which is way more than whatever liquefaction suggest us.
Yes, but they did a test up to 20% of the shear strain, but for the liquefaction triggering, they counted the number of the cycles to get the 3% of the shear strain.
So the number of counts is corresponding to
The
shear strain equal to 34.5?
Yeah,
3.5.
yes,
Okay.
which is the criteria for the liquefaction triggering.
Okay, yeah, sounds good. Thanks.
Go ahead, Navid.
Thank you very much for your presentation. I want to ask, in real world application, how do you intend to apply this in the soil environment? Like, are you going to inject the chemical, like with using borehole, something?
Yes, that's a good question. So for oh. So for the lab test, to do the MICP treatment, we injected the fluid from the bottom to top and top to bottom. But we can do it because it's in a very small scale, but in the field, we can't do it. So the industry people are saying we can install the one borehole for the inlet and insert the other borehole for the outlet. So if you're injecting chemical solutions into the inlet and taking out it from the outlet, then you can create the flow from the inlet borehole to the outlet borehole so that you can let them do the chemical reaction.
Thank you very much. Also, I wanted to know, what is the time for this chemical to get hard? Like, also the depth, time, and humidity of the soil affected or no?
Oh, so basically we are using a bacteria, so it's affected by lots of various factors like temperature, pH, and everything. But in an ideal condition, in a lab condition, it also depends on the concentration of the chemical solution that you use. But for our recipe, it only takes like 8 to 12 hours to use like 80% of the chemical that we injected. But if you want to apply this technique to the field, then you need to get the core from the field, and then you have to do some lab tests to find the optimum treatment condition. But definitely it will affect it by the soil natural properties as well.
Thank you very much.
Yeah.
Go ahead.
Thank you very much for your presentation. I read some application of MICP in the mining industry, actually in mine tailings. Are you planning to do some research in the future in this kind of materials?
If I have a plan to do some mining failure research, I'm not, because my research interest is mainly focused on the soil erosion and the liquefaction triggering. So actually, I'm trying to apply the MICP technique to the dam overtopping erosion problem. So my answer would be no, but I believe that someone will keep doing a research on the mine tailings as well.
Okay, thank you.
Thank you.
We got any other questions or any questions from people online? Sweet. So I'll cut that as the end of questions. And to thank you for your time. We got you a little something, and by we I mean Dr. Mataman, but
Thank you so much.
thank you. So with that, that's the end of the seminar. Thank you everybody for showing up.